Hmm. Okay, ladies and gentlemen, here we are. We're going to talk about sequences today. This is from chapter 13. In particular, we're going to begin with something called an arithmetic sequence, also known as an arithmetic progression. So I'm going to read pretty much from the notes. We'll do some explanations, and the right panel on your screen will be some selected problems which I thought would be worth looking at in more detail. Okay, so an arithmetic sequence is a sequence. Sequence is a list, right, of numbers in which each latter term is formed by adding a constant number to the previous term. The constant number is called the common difference. We symbolize it by D in most of the formulas we'll be using. And just a side note, D may be positive or negative. So it's just some simple examples here. Find the common difference. Well, I just look at it. It's going up by 3, so the common difference is 3. How about here? Well, it's going down by 30, so the common difference is negative 30. And let's look at this one. Well, let's see. This is going up by 3, up by 5, up by 7, up by 9, dot, dot, dot. So we don't have a common difference. Therefore, this is not an AP or an arithmetic progression. All right, so not all the sequences that we'll be dealing with are arithmetic progressions, and you have to watch out because certain formulas apply to certain types. So, don't be caught off guard. Okay, so let us look at a formula. And the formula here is for the nth term of an arithmetic progression. And here it is. I'm going to try and explain it. Pretty easy to understand, really. But L stands for the last or the nth term, so it could be written in this form as well. And you start out with the first term, and you add n minus 1 common differences. So if you want to get the 12th term, let's say, you would start with the first term and you would add 11 common differences. If you wanted to get the 100th term, you'd start with the first term and add 99 common differences. And basically, if the first term is A, the second term is A plus D, that's the common difference. Third term is A plus 2D, the fourth term is A plus 3D, the fifth term is A plus 4D. And notice that the coefficient in front of the D trails the term number by 1, because if you're already at term 1, you add one common difference to get to the second term. You would have added a second common difference to get to the third term, and so on. Okay, so with that in mind, let's look at an interesting example. Now, not all the examples are going to be numbers, but we can often pattern them after numbers. So if the patterns illustrated below continue indefinitely, notice the dots, the dots, the dots. That means it goes on forever and ever. Okay? Find the nth term formula for the number of square tiles in the nth figure of the sequence, and in particular, find the 8th and the 23rd. All right, well, I think easy way of doing it is just putting in the numbers. Count. You have 2 tiles, you have 5 tiles, you have 8, you have 11. And clearly, this is going up by 3. So this is an arithmetic progression, and it is modeled by what we've been working with. So let's go ahead and let's see if we can work this out. A formula for the nth term. Well, we're going to use the idea that the nth term is A plus n minus 1 common differences. So if you do that, and of course we start here, n is 1, 2, 3, 4, 5, so the would look like this basically. Okay, so you can sort of work that out for yourselves. What formula seems to give you a 2 when n is a 1, a 5 when n is a 2, an 8, right? So it looks like 2n plus 3n actually minus 1. 3 times 1 is 3, minus 1 is 2. 3 times 2 is 5. So the amount that we're going up by actually plays the role of the coefficient here. So it's 3n minus 1. So if you have 4 terms, 3 times 4 is 12, minus 1 is 11. Okay, now let's pretend you don't see that. Okay, what you could do simply is this is the tile pattern, writing it out in longhand, 2, 5, 8, 11, 24. And just to make it clear, we're starting with n equals 1. That's how humans started counting. 1, 2, 3, right? 0 was a very complex concept, didn't come about till much later in human development, or so we think. So n is 1, n is 2, n is 3. So this would be symbolized as a sub 1, a sub 2, a sub 3. This is the first term, the second term, the third term. And here's our formula. Okay, we're just plugging the numbers. The first term is a 2. The common difference is a 3. And if you're looking for the 8th term, you'd have to add 7 common differences, so you get 23. So the 8th term would be a 23. You could write them out, of course, but it's easier to use the formula. And to get the 23rd term, well, again, it's first term plus n minus 1 common differences. So you get 2 plus n minus 1. Well, if you're going for 23rd term, n minus 1 is 22. You're adding 22 copies of 3. So that's 66 plus 2 is 68. Okay? And then doing something which we had a little bit new, let's aside find the sum of the first 23 terms. Well, here's a good way of handling it. And there's an apocryphal story about a man named Carl Friedrich Gauss, who came to be one of the greatest mathematicians of all time, up there with Euler and Newton, some of those guys. And supposedly he had a problem similar to this as a little child. Teacher didn't want to be bothered, and so the teacher asked to write, to add up the whole numbers from 1 to 100. And the kids would write it out on slates. This was in the 1700s, bring it up to the teacher's desk. And Gauss came up with what we believe is the following method. He was like 8 or 9 years old at the time. Here's what he did. He wrote the numbers out forward. Okay, so 2, 5, 8, 11, dot, dot, dot. We got a pattern. We don't have to write them all out. And the 23rd one we just found is 68. And then he wrote them down backwards. And he noticed something. The numbers here are going up by 3 as you go from left to right, and here the numbers are going down by 3 as you go from left to right. So therefore, the sum must be the same. So 2 and 68 is 70, 65 and 5 is 70, 62 and 8 is 70, so forth and so on. So since we're adding up 23 numbers, we have 23 copies of 70. That's 23 times 70, but we did it twice. That's 2s. So if you work this out, 23 times 70 divided by 2 is 805, and we're going to learn later that we have a little formula for it, and this formula is attributed to Carl Friedrich Gauss, otherwise known as Gauss's rule. And it says you take the first term and the last term and add them up, divide by 2, which we have a name for that called the average, and you multiply by the number of terms. So you take the average and multiply by the number of terms, and that basically gives you the result. Okay, so we're going to move along here, and let's see, we looked at these, and a little formula here which we'll come back to later on, but basically that's what Gauss did. Here, this is what Gauss did. If you want to find the sum, he wrote the terms down, a plus 1 common difference, a plus 2 common differences. Last term is L. This will be L minus a common difference, L minus 2 common differences. You wrote them down twice. And again, notice every column adds up to A plus L. There are n columns, but we did it twice. So divide by 2, and here's your formula for the sum of the terms in arithmetic. And that's the form we basically use. But at any rate, let's do some examples. Okay, and the one that I want to do, and I'm illustrating, I want to do number 2. So number 2 here says find the 20th term in the arithmetic sequence 32, 25, 18, 7. And the first thing we'd like to do is verify it is in fact an arithmetic sequence, so we want to see if it goes up or down by the same amount as we go from term to term. So down 7, down 7, down 7. So at this point, assuming that the pattern is continued, we're going to say, yes, it is an arithmetic sequence. First term where a value is 32, the common difference d is negative 7. And here is our computation. Find the 20th term. We use our formula here. And 20th term, you can write as an L for last term, but for us we're writing it as a sub 20 for 20th term. Is the first term, 32. Plus, if you're looking for the 20th term, there'd be 19 common differences because we started the first term, right? So 19 times negative 7 is negative 133, and if the 32 is negative 101. So we know that without actually writing them all down, which would be ridiculous. Okay, next one I want to look at is number 3. Which term, in other words, the 8th, the 10th, the 50th, the 90th, right? Which term of the arithmetic sequence is equal to 151? So let's see, let's just verify. Well, we're told it's an arithmetic sequence, so we know, therefore, that it has to have a common difference. So the common difference is obviously 6, going up by 6's here. So we write our formula down. The nth term is first term plus n minus 1 common differences. The term we're looking for is 151. In this case, we're looking for n, right? So you get 7, first term, plus n minus 1 times 6. You multiply this out, 6n minus 6, so you end up with 6n plus 1 on the right side. So if that's a 151, then 6n is 150, n is 25, so the 25th term would be 151. Okay, so we've already seen this formula for the sum, and just let's look at the symbolic part here. S is the sum of the first n terms. I sometimes use S sub n. A is the first term, L is the last term. We could also use A sub n here for the nth term, and it's the number of terms. And I'm going to prove this using Gauss's rule, and I think we already did that. I just want to show you that, in fact, at the end of this, do I have the, oh, I don't have the formulas here. Okay, so in the other version, the sequence notes, I do have the formula derived, the proof. Okay, so let's take a look here, and let's do some problems. And actually, this is the proof here that we just did, though. Okay, so let's take a look, and we're looking at summing the terms of an arithmetic progression. We'll take a look at a couple of these. Let's look at number 2 first off. Okay, so in number 2, first row of a movie theater, let's say it's 36 seats. Each succeeding row has 2 additional seats, so you have 36 seats, and next row it opens up. Okay, an amphitheater type arrangement, I guess. Has 38 seats, and then 40 and 42 and 44 and 46 seats. The theater has 40 rows. How many seats are in the last of the 40th row? Okay, so here we go. Let's write our formula down. 40th row is A plus n minus 1 times D, so n minus 1 common differences. We're told here the common difference is 2. So if n is 40, there are 39 common differences added to the first row of 36. So this is 78. 36 and 78 is 114. So these are the number of seats in each of the 40 rows. This is the number of seats in row 1, row 2, row 3. This is the number of seats in row 40. And knowing that the common difference is 2, we could work backwards. The 39th row would have 112 seats, so forth and so on. Okay, part B, how many seats in the entire theater? Well, that means adding up. So this is what we want to do for part B. Okay, so let's do this in 2 different ways. I want to do this using Gauss's approach, what we think was his approach, and I want to do it by using the formula. I think real life I probably use the diagram a lot more than the formula, but at any rate, so here we go. This is what I want to add up, and I'm going to notice the first and the last add to 150, the second and the next to last add to 150, the third and the you know, penultimate one actually add up to 150. So each pair here are going to add up to 150. Well, how many pairs do I have? If there are 40 rows, I have 40 over 2 or 20 pairs. Each pair sums to 150. So using a Gaussian common sense smart way of doing it, 20 times 150 are 3,000 seats. This theater holds 3,000 seats. Now, some people see it like this. Other people like formulas. So let's do the formula instead. Here's the formula. So I'm using S sub 40 to mean the sum of the first 40 rows, and N over 2 times A plus L, where L is the last row, in this case it's the 40th row. So notice that in either case I need to know the number of seats in the last row. So I basically had to compute this in either case, whether I was doing it by common sense Gauss's rule, or whether I was using the formula version. Either way. Okay, so let's put in the numbers. N is 40, so this is 40 over 2. First row is 36, the last row is 14. Now work this out. 36, 14 is 150, and again, this is, 20. Or I could have gone 2 into 150, 75, multiplied 75 times 40. Either way, I get 3,000. So it's good to know that the common sense approach gives you the same result as the learn, memorize the formula approach. Okay, let's do one more, and then we're going to turn our attention to geometric sequences, different type, very important, in the next video. Okay, so question number 3. Find the sum of all the multiples of 3 from 1 to 100. Okay, well, so here we go. Write them down. All right, 3 and 6 and so forth up to 99. And take the common sense approach again. We have 3 and 99 adds up to 102. 6 and 96 adds up to 102. They add up to 102. Okay, so in this case we have an odd number. We have 33 numbers, right? Because if I divide by 3, I can see this is 1 times 3, 2 times 3, 3 times 3, 33 times 3. So I have 33, and it's 33 here. Adding up 33 over 2 times 102. So 33 times 51, 1683. So these numbers add up to 1683. Okay, and the formula, of course, would be this one. So n over 2, we're just, you get the exact same results here. Okay, so whether you use the formula or not, you get the same results. Okay, number 4, I'm just going to give you a few hints on what to do. But this is Gauss's rule, where you just add up the numbers starting from 1, the common difference is 1. So if you want to add up the numbers from 1 to n, like 1 to 10 or 1 to 100, you'd write them out from 1 to 10, and then you go backwards. From 1 to n rather, and you go backwards from 1 to n this way, and each column is going to add up to n plus 1. And there are n over 2 columns, so this is the formula. So if you wanted to get the sum of numbers from 1 to 10, you'd have 10 and 1 is 11, 10 over 2 is 5, 5 times 11 is 55. You want to add the numbers from 1 to 100, which we believe is what Gauss was asked to do by his teacher. I would never do anything like that, I'm not that mean, but Gauss had a mean guy. Alright, 5, so if n is 100, I'd have 101, 100 over 2, so 50 times 101, 5,050. Okay, so that's how we think Gauss did it. It's apocryphal, cool word. It means we really don't know, but it'd be nice if that's how we really did it. But the story goes, he handed in his slate almost instantly. He knew the trick. Okay, so we're going to stop here. We'll pick up geometric sequences next time, and we'll take the same approach. We'll do some selected problems, and if you have the sequence notes with the plus form, then you've got all these little annotations in here. Okay, so see you later.